When a beam is loaded with point loads or distributed loads, it will bend, maybe a little, maybe a lot. In Chapter 10, we will learn how to calculate how much a beam deflects under load. In statics class, a couple of the basic assumptions were that nothing moves, well, nothing accelerates, and no dimensions change. When you solved for forces in trusses using the method of sections or the method of joints, you assumed that all the truss members had a fixed length, and the angles of truss triangles did not change. In strength of materials, we agree that dimensions can change. Tension members stretch, compression members shrink, torsion bars twist, and beams bend. We are going to start with a very unusual case where the bending moment is constant. There's a derivation in the book that you can read, but let's just skip to the result. If a beam is under a load that produces a constant bending moment, then the beam will take the shape of a circular arc with a constant radius r. We can calculate r if we know Young's modulus, the moment of inertia, and the bending moment. Let's look at an example of a beam with a constant bending moment. This is a 1-inch nominal diameter Schedule 40 steel pipe, so we can find the moment of inertia in Appendix D. Between points A and B, the bending moment is constant, so between these 2 points, the beam bends in a circular arc. The shape is different outboard of the 2 support points, because the moment is not constant to the left of point A or to the right of point B. So, the radius of curvature of the center part of the beam is 90.938 feet. We can use this number to figure out the maximum deflection of the beam. Let's use the Greek letter capital delta to be the deflection of the beam. At the midspan, delta is r minus h, where h is one leg of a triangle that has the radius of curvature as its hypotenuse. The other leg of the triangle is half the distance between the supports of the beam. Use the Pythagorean theorem to find h, then subtract it from r to find the deflection at the midspan. This beam is deflecting a little less than 5/8 of an inch. Here's another example. A bandsaw consists of a flexible saw blade that wraps over 2 circular drums. The drums rotate, causing the blade to move. You can think of the saw blade as a very thin beam, where C is half the thickness of the blade. The portion of the blade that is running over the drum is being bent with a constant radius. Therefore, we can use our equation r equals EI over m. Rewrite it to solve for moment, then substitute the result into the bending stress equation. We find that the bending stress equals Young's modulus times c divided by r. We can use this equation in a couple of ways. One way is to design the blade so it doesn't snap as it's running over the drum. If you know the allowable stress for the blade, Young's modulus, and the size of the drum, you can work out the minimum blade thickness. Another way to use the equation is to design the saw. Given a particular blade thickness, width, and allowable bending stress, you can figure out the minimum drum diameter that will work. If the drums are too small, the blade will break. If the drums are too large, then you might not be able to fit the saw into your workshop. The curvature method is useful for finding deflection when moment is constant, but you know from experience that m is almost never constant in most beam problems. Fortunately, engineers have worked out formulas for calculating deflection for many loading cases. You have many of these formulas in Appendix F. The formula method is a three-step process. First, look in Appendix F to find a loading case that matches the beam problem you're trying to solve. Next, pick the beam deflection equation that applies. You may have one equation for deflection at a particular location, such as the end of a cantilever beam or at the location of the point load. Then it's just a matter of solving the equation. Some beam problems won't match any of the loading cases in Appendix F. However, if a combination of more than one loading case matches your beam problem, then you can use the principle of superposition to solve the problem. Here is a nominal 4-inch diameter Schedule 40 steel pipe. It's 10 feet long, and there's a 4-kip point load at the midspan. From the appendix, we can find the moment of inertia and Young's modulus. The first loading case in Appendix F is a point load at the midspan of a simply supported beam. We can use the formulas in this case to calculate the reaction forces without having to calculate some of the moments or some of the forces. And we can calculate the maximum moment without drawing shear and moment diagrams. The maximum deflection is equal to PL cubed over 48 EI, and it occurs at the midspan. It works out to 0.664 inches. If you want to know the deflection somewhere else along the beam, you can use the equation at the bottom of the screen where x is the distance from the left end of the beam. Let's take the same pipe without the point load. Then it will sag under its own weight, which we can find in Appendix D as 10.8 pounds per linear foot. The maximum deflection for this loading case occurs at the midspan, and it works out to 0.011 inches. What if the loading case is not in the appendix? Here is our 4-inch pipe again, but now we want to know how much it deflects at the midspan due to the point load and the weight of the beam. The principle of superposition says that at any given location along the beam, we can add deflections, shear loads, or moments, but it has to be at the same location, which in our problem is the midspan. The total deflection at the midspan equals the deflection at the midspan due to the point load, plus the deflection at the midspan due to the pipe's weight. It works out to 0.675 inches. The point load is contributing about 98% of the deflection, and the pipe's weight is contributing the last 2% of the deflection. We have to be really careful about applying the principle of superposition. It only works at the same location along the beam. You cannot add the maximum deflections or maximum moments if they don't occur at the same location along the beam. This beam has a point load that is not at the midspan, plus it has a uniform distributed load. For the point load, the maximum moment occurs at the point load. For the uniform distributed load, the maximum moment occurs at the midspan. You cannot add the maximum moments of the two diagrams because they don't occur at the same position along the beam. The maximum deflection also occurs at different places along these beams. You can add deflections at the midspan or at location x equals 3 feet, but you cannot just add the maximum values. Here is a case where the formula method looks like it's not going to work. We want to know the deflection 4 feet from the left end of the beam. The formula for deflection is only good for x is less than a. But here, x is greater than a. The way to solve it is to flip the beam around and solve for the mirror image of the beam. We will add an apostrophe to each variable that changes. The apostrophe is called prime. I don't know why it's called prime, but that's the convention. Now, a prime is 8 feet, b prime is 2 feet, and x prime is 6 feet. What if we ignored the limitation that x has to be less than a? The deflection is proportional to a function of b, x, and L. The other terms don't change, whether we flip the beam or not. If we solve the b, x, and L portion of the equation, we get the number 640. Don't worry about units. They are also the same whether we flip the beam or not. If we do flip the beam, then the deflection is proportional to a function of b prime, x prime, and L. Solving, we get the number 720. Divide the two results and we see that not flipping the beam gives an answer that's 11% too small. The error is even greater at the midspan, where the deflection calculation would be nearly 40% too small. This shows why it is important to flip the beam if the formula is only good over a portion of the length of the beam.